well. I shouldn't have started it yet because I got to hand out the thingy. All right, if you were gone on, wait, hold on. Let me try my bearings. There was a quiz on Friday, right?
Yep.
So if you were absent, make sure you come make that up sometime this week. We're going to move on to angular momentum. This got butchered in the printer, so there's a little bit of like, hopefully the formatting is not too confusing. But there's 6. Can you pass that? Just pass that back. And then here's one for Taylor and Zach. And
Oh.
okay.
These are going to mildly inconvenience you.
They're still in order, and nothing got like removed, but there's like a blank page that got inserted, and then one of the diagrams got like pushed to the next page. Other than that, it's like, oh, and then number 23 got split into 2 pages. So yeah, kind of annoying, but it's my fault for not double checking the PDF file. Oh, and I gotta do. So while I'm doing attendance, read that first question. It kind of explains what we're doing in text form there. Lindsay's gone. Let's see. Winslow. Winslow's always gone. Julia's gone. All right. Okay. So, just walk through this first question here. So it says there's a quantity called angular momentum, which is, we use the letter L for that. Man, Mr. Coleman's booming voice just, makes me feel at home, you know? It's comforting. He'd be that guy back in like feudal times who like announced the king was coming. Like, what is it called? Heralds? Is that what it's called?
So, yeah.
Anyway. There's a funny word, stentorian, that I can't remember. Does anyone know the origin of that word, stentor or stentorian? It's like a mythical thing. Whatever.
I'll look it up.
I think it's a guy that was like mythically loud. There's a word, stentorian. I remember looking up. I was like, what the heck does that mean? And it was a reference to some myth that I didn't know. But anyway, okay. Angular momentum is the radial value times the momentum. So you might go, okay, well, this guy, he's traveling in a circle. So he has, you know, he's traveling at some radial distance from this axis of rotation. And he's also traveling with velocity. And so you could associate his velocity with a momentum, right? So we know that's just momentum. And we know that momentum is defined as mass times velocity. Just remember that. So how can you have a big momentum? You can be really heavy, or you can be going really fast, or both. You can be like a meteor, be really heavy and go really fast, right? Yeah, you have big momentum there. So then anyway, so you go, okay, well, this is the definition of angular momentum. So what this tells you is that if you like maintained your linear velocity and maintained your mass, but then like moved farther away from the center, so if you increase your R value, you'd have a bigger angular momentum. Okay, so anyway, let's write, the first question asks us to write this in terms of I and omega. So let's do a little bit of math here. So you'd say So replace this momentum term with mv. And then who's got a thought of what we would do next? Anyone? Or maybe just, can you identify which of these letters do I want to not to be there anymore? The V, right? I don't want V. I want this to be in terms of I and omega. So we know, who remembers this one? V, how do I relate V to omega? Yeah, V equals omega R. That's an importante right there, right? That's a kind of central to all things rotation, right? So, so replace the V with omega times R. And then if we regroup our terms, R times R is R squared. Now let's see, does anyone remember? Hopefully. That's I right there, mr squared, for a point mass at least, right? For a solid disk, it's 1/2 mr squared, m being the total mass of the disk, that kind of thing. So look at that, that's a beautiful little formula there that comes out. Well, actually, I mean, it's not a coincidence. This is sort of one of the reasons why we define I to be mr squared, just because, like, look, it works out perfectly. You get this really nice momentum equation because, like, look, our basic definition of momentum is mass times velocity. So our rotational momentum, or our angular momentum, is our, like, remember I is like your rotational mass, it's your rotational inertia multiplied by your rotational speed. So it's a perfect analog, right? God, we're so glad to be back. We are so energized, especially Trenton. The patriotism is just bursting. Out of it. Right? Trenton. Okay, so anyway, I hope that makes sense. That there's a perfect rotational analog to momentum called angular momentum, and it's just the inertia times the speed. Rotational inertia times rotational speed. Okay. So B and C are going to ask us to, so let's see, write an equation for the system's rotational period in terms of L and I. So I'll give you a second to think about that one. How do you answer a question like this? An equation for the system's period T. So suppose we knew L and I, and I wanted a nice formula that goes from the L and the I value and just tells you the period. Do we remember what period is?
It's the time it takes for.
Yeah, the time it takes.
Revolution.
The time it takes for one revolution. Yeah. So if the period was 5 seconds, that would be, takes 5 seconds to make a full revolution. Right? You're so tan, I didn't realize. Did you go to Hawaii or something?
Florida.
Florida. Okay, sweet. How was that?
Good.
Did you meet Florida man? No, you had no Florida man encounters? It's disappointing. Yes.
Have you seen the meme where it's that someone writes sine divided by cosine on their arm and says they got tan as well?
So savage. That's a big blue moon right there.
What's your thought on the memes about the stuck boat?
I haven't seen any memes about it. There's a boat blocking the Suez Canal.
Yeah.
Memes about
It's pretty amazing.
Haven't seen the
Well, I don't know. Four be the memes. I'd love to see a meme.
I've seen a good amount. Yeah. My favorite is the character.
Okay.
So,
So the answer to B is actually pretty simple. You start with your previous result. You say, well, I know there's a relationship between omega and the period, right? Huh? Say it.
Oh, sorry.
So remember, like omega is the radians per second, right?
Yeah.
So anyone remember the relationship? 2 pi. Should that be it? Should that be right? So for example, let's say the period was 5 seconds, just for example, 5 seconds. That would mean that if it does one full rotation in 5 seconds, that means that you did 2 pi radians, because that's how many radians are in a full circle, divided by 5 seconds. So that would be your radians per second speed. So that's the same as, I should say is I can now substitute that in, right? That can go in there. And so my relationship here would be L equals I times 2 pi over t. Now, do I have my equation involving the things I want it to involve? Okay, let's solve for t. So multiply both sides by t. Like that. And then divide by L. Regard this as 2 pi times I over. Okay. Do we feel okay about that?
Yeah.
So what that means is that for, say, a given I value, so say you had a certain object with a certain I value, certain inertia, if you increased the angular momentum, that would correspond to a decrease in the period. And does that click with your understanding of how things spin, right? So more momentum would be like faster. So keeping the object the same and making it go faster would be the same as saying like you're going to decrease the period. Okay, so next is what if we exert a torque on the system over a time period t, so torque tau, fancy Greek t, and then over some time period t, regular American t. And then we're going to say what's going to be the increase in the change in the angular momentum. Okay, so let's see. Well, first, let's look at how torque equals I times alpha. That's Newton's. That's basically F equals ma, but for the rotational version of that. Okay, so we got our tau in there. So our goal for this one is we want our equation to involve torque, time, and the change in angular momentum. Okay, makes sense? So how can I replace this alpha then? Because I don't want alpha in my formula. Very good. The change in angular speed divided by time, right? Acceleration is change in speed, change in velocity divided by time. Cool beans? Okay. And then, wait a second. Look at that.
Oh, you can sub in L.
Well, most of the time, I is not going to change. I mean, we'll go over some stuff later. You can change the I value by changing the shape of the object, if it's something that can change shape. But usually it's just, if I stays the same, then the change in momentum is equal to I times the change. That makes sense?
Yeah.
So what that means is that I can replace this I times delta omega with delta L. And so the change in, let's rewrite it like this. Let's see if anyone remembers the word. There's a in the regular linear version of this, there was a special word that started with an I. I'll write it up here. We talked about how the change in momentum was equal to the net force times time. Anyone remember the name for that? Starts with an I? Hangman.
Impetus.
Huh?
Impetus.
That's a different one. That impetus is what the ancient Greeks thought caused motion, but then we were like, actually, Newton was like, well, actually, things that are in motion just tend to stay in motion. What really we got to focus on is force that causes a change in speed. Impulse.
You guys probably be a little bit harder than that.
Impulse. Good job remembering impetus, though. That's a fancy word.
Oh, sorry.
Fancy word of the day. So anyway, this is in a sense. Do you guys see the analogy there? So the change in linear momentum is equal to the net force multiplied by how long does that force get applied for. And then the change in angular momentum, so in a sense like an angular impulse, is the torque. It would be the net torque. If you had more than one torque involved, this would be the net torque multiplied by time. So again, a perfect analogy. Isn't that beautiful? Huh?
The angular.
Yeah. I'm not sure if I've ever, that might be a word. I don't know. I haven't heard that. I haven't read that very often. I've read impulse many times, but. Okay, so anyway, that's a formula describing the relationship between a change in angular momentum and a torque and a time at which that torque is applied. So definitely this is an important formula. This is a very important formula, and this is the definition. Okay. This one was just kind of an exercise. We're not gonna, you might refer to that possibly, but probably not. Okay. Why don't you try to answer number 2 on your own? And a hint for that one is, what's the relationship for if something's rolling? How can you relate its velocity to its angular velocity?
Well, V equals omega R.
V equals omega r. So for number 2, try to figure it out. My other hint to you would be maybe this. This is a good place to start. And then using this and the fact that for a rolling object V equals omega r, you can answer that question.
Paul, what do you call it when something you're exerting a torque on a system and then that torque like suddenly comes to a stop?
I don't know.
Call it stubbing your toe.
It's pretty good.
Oh.
That's pretty good. I like that one.
No.
Oh, how tired are you right now?
I'm tired?
Yeah.
I don't feel that tired. Why? Do I look tired?
No.
You let that get up, go.
Yeah.
It was funny.
Paul, you're so.
This peak comedy right there. All right. Who got an answer for this one? Who feels like they know it? Anyone? Colin?
L equals KMR squared times V over R.
Like that? Yeah. I times omega. And then maybe, R squared divided by R. It's the same R, right?
Yes.
So yeah, that's correct. And then we can do maybe one more simplification. So K M times R. Kind of a weird formula. You don't see that very often. It's a product of 4 terms. What's interesting there is it tells you that for a rolling object, there's these sort of linear relationships going on. If you double the mass, you'd be doubling the momentum, the angular momentum. What you're going to find for a rolling object, it's kind of interesting, is that a rolling object has linear momentum, like the fact that it's moving through space, and it also has rotational momentum. So there's 2 things going on at the same time, which makes it complicated to analyze sometimes. But
What does K represent?
K is that, so remember how we had like, say for a,
Oh, yeah.
kind of blanking on, for a solid sphere, so the I value for a solid sphere, I think is, what is it, 2/5, I think?
Yeah,
Yeah.
something like that.
2/5 mr squared, where m's the total mass of the sphere or the ball, and r is the radius of the ball. And then, so this, you can call this like sort of a K value. And certainly, it's not the K value for a spring constant, it's just some arbitrary.
Yeah.
We use K a lot in math and physics to be like, it's going to be some constant. Because a lot of symmetrical objects, you can write them in this form: some constant times mr squared. Not the tetrahedron, as we saw, but sphere, cylinders, discs. Okay. Doing okay, Julia? Oh, looking at your wistful faces, man, really just
I think that's enough.
makes me glad to be at work again. Okay, so number 3 should be pretty straightforward. You're probably going to want a calculator for this one. It's just a little bit of practice in calculating the angular momentum of each object. Now, I didn't write you the I values, so maybe let's just jot those down real quick. So solid sphere was this. What was solid cylinder was, I know that one, 1/2. Do you guys see why you're going to need these to calculate the momenta? Because you need I and you need omega. So if it's a point mass, you can use this formula if you know if you can calculate the and then we had what, a hollow sphere was 2/3, and a hollow cylinder is just mr squared, so same as a point mass. So maybe jot those down on that page, and then you're gonna just calculate them. I feel like those should be. You can save those, maybe do those at home or save them for a work day. But let's look at 4. I do want to touch on conservation of angular momentum before we move on. So before the class. Okay, so let's look at 4. 4 says you have a spinning solid disk with a radius of 50 centimeters and a mass of 40 kilograms. And it's making 12 rotations per second, and then some brakes are applied. The wheel comes to rest after 6 seconds. Okay. So the first question is, what was the torque acting on disk? So, by the way, if you read part B and part C, just to look forward, it asks basically how much force was acting on how much force was the brake pad exerting on the disc if the brake pad was on the outer rim of the disc versus halfway between the axis of rotation and the edge. So does it make sense why to talk about just the torque required to do this it's not really relevant where the brake pad is. Like, you guys all know bicycle wheels, right? You guys know how in the old days, well, I guess they still do make some bikes like this, but where does the brake touch the wheel? Out here, on an old-fashioned bike. But nowadays, they put this disc here and the brake pad contacts there.
Yeah.
Cooper, is that alien to you? Have you seen
Yeah, I've
that?
never seen that before.
Oh, really? Yeah, it's like disc brakes versus, what do they call it? It's like a caliper brake or maybe the rim brake. Anyway, so what's interesting is you actually, I mean, which one requires more force? So say you want to exert, let's say for argument's sake, I want 100 Newton meters of torque.
The outside.
Which one takes more force, out here or in here?
The other ones never have any grip, so.
Well, what's interesting is this actually requires a lot more force because look at the definition of torque. Torque equals radius times force. So the bigger your radius, the smaller your force required to get the torque you want. So actually, you get a lot more torque for a given force out here, but there's other reasons why they do that. I mean, you can generate more force with this kind of disc brake, and it's supposed to be more stable and stuff, and better in wet conditions. All sorts of other like little engineering reasons why most bikes nowadays have these disc brakes. Anyway. And your car too. Your car has the same kind of similar principle. You got brake caliper, go squishy, squishy. Anyway, where was I? Oh, so in this question, it's asking. I don't know. I guess I just wanted to see if you guys understood that it's irrelevant. The positioning of the brake is irrelevant if I just want to know how much torque was needed to generate this change in speed. But if you want to know how much force the brake required, then you do have to know where it was positioned. Okay. All right. What's the torque? Okay, well, that's fine. We can actually solve this problem using the Newton's law, but I guess we can kind of do it however we want. So let's start calculating a few things that we're going to need. Because let's look at an important formula we just derived, or at least I claimed it was important, was that the change in angular momentum is equal to the torque multiplied by the time, right? So why would I write that down? Well, I think we could calculate the momentum of the disk, right?
Yeah.
And we know how much time that was exerted, that the force was exerted for, so that there's the torque right there. You get the torque. Okay, so let's calculate. Now, of course, this change in angular momentum, it's going from some speed down to rest. So this would really just be how much angular momentum did it start off with.
Yeah.
So for a solid disk, that's, it's I times omega for anything. And then the I value for a solid disk is 1/2 m² squared. Is this, you guys still with me? Does that make sense?
Yeah.
I'm getting involved all the letters that were given to us so that we can then just plug in what we know. So let's go ahead and get the I value. Well, 1/2. What's the mass of the disk? It's 40 kilograms. And the radius is 0.5 meters, 1/2 meter. So that's 1/4 times 40 is 10, 1/2 of 10 is 5. All right. Here's a big brain question. What are the units? I'm trying to be really good and show my work here. What are the units of I?
I would say like kilograms.
Kilograms times
Meter squared.
right? So it's kilograms times square meters. Okay. But so this number here, the I value is just 5. Right? Makes sense? What I'm doing there? How about omega? What was the omega before this thing started? Well,
12 pi.
close. They're giving us 12 rotations per second.
Oh, shoot. Okay.
That's what letter is that, by the way?
That is,
Yeah. And so
So it's
omega,
4 pi.
24 pi radians per second. Okay, so my omega change, I went from 24 pi down to 0, so that's going to be 24 pi. Roughly 75-ish, I'm guessing, 76-ish, if you multiply that. Torque is what I want to know about. And time was 6. So the torque is 20 pi, which is roughly, I mean,
52.8.
yes.
6.2.
Yeah, 62.8 roughly. Units of torque. So remember the units of torque, remember the definition of torque. Newtons times meters. NM. Brings me back to the good old days of AOL Instant Messenger. You guys know about that? Get home from school, go on your computer, and your friends would sign on. You'd be like, sup, NMU? NM. Not much. Rich conversations were had there. Sup, NM. NMU? Okay, so from here, the rest of the question is actually pretty easy, right? Because this is how much torque was needed to stop the disk in 6 seconds. By the way, let's say you increase this number. Let's say it's instead I said, oh, we don't need to stop the disk in 6 seconds. We can stop the disk in 10 seconds. What does that do to the torque required? It decreases it, makes it less. So if you say I'm okay with the disk stopping more slowly, then that's less torque needed. If you decrease this number, if you say I need the disk to stop in 1 second, then you need more torque, right, to achieve that. So back to the bicycle thing. I have a bike. Do you want it to stop fast or slow?
Yeah.
Well, you want the capability of stopping fast, right? You want, if the user presses the brakes as hard as they go, then you want to stop as quickly as possible. So you want this to be a small number and this to be a bigger number. So, but yes, you don't want them to tap the brakes and have it slam to a stop. My friend's car in college did that. If you like touch the brakes, you'd like oh, you had to have like the ultimate soft foot, yeah, to operate the brakes. Okay. So if a caliper was out here, and we're going to do this calculation, torque equals force times radius. What's the radial value if the caliper is way out here?
0.5 meters.
0.5 meters. So I know the torque. And I know the R value. So I guess the force. Look how it all works out with the units. The units of this was Newton meters, and the units of this is meters. Newton meters divided by meters gives you newtons. That's nice. Isn't that nice?
Yes.
So what, 125.6, I think? So nice, 125.6. However, if you instead, so for part C then, if instead you put the brake pad in the middle, what's the R value now? 0.25. And so look what happens. Same torque, different R value. That's right. Okay, so moral of the story there is, and maybe you already noticed this, but if you did a good job, that if you have the radius, you have to double the force. Right? Cutting this in half doubles this. Okay. I guess we'll do conservation of momentum tomorrow. You guys seem
Sounds like a good plan to me.
I'm not gonna work a movie,
you're in the working mood. Yeah, we'll do it tomorrow.
The one
Okay.
time you were really working.
Well, we have some time here, guys. Why don't you just knock out these questions so you don't have them for like homework? Okay.
That's not reasonable.
All right.